Good morning, grade 12s. Let us carry on with our trigonometry segment so that those of you who are sitting for these June exams can have enough to go on with. So 5.1, we are given cos of 40 degrees is equal to P. So always show this as a ratio so that we can do our terminal arm. Okay guys, so there's our terminal arm. We can see cos 40, it's an acute angle, so it's already placing us in the first quadrant. So that's why our terminal arm is on the first quadrant. And as we can see here, sine is defined as opposite over hypotenuse. Therefore, that means P is the opposite side. The hypotenuse is 1. When the terminal arm is 1 unit, we call this a standard circle at the center, at the origin. All right. Then we use our Pythagoras to work out our corresponding x part, which is going to be 1 minus p squared. Okay, easy. So this is fairly standard. 5.1.1. We need to handle sine of 220 degrees. This is the same as sine of 180 degrees plus 40 degrees. So reduction formulae are always going to be applied. So every time you see an angle greater than 90 degrees, reduce it to an acute angle equivalent. So sine is negative in the third quadrant. Then we take the acute angle equivalent. So this becomes minus p. That's the answer. Because it's literally p over 1, but now it's negative. So this reduction and the answer is the first 2 marks. 5.1.2, we've got to do cos squared 50 degrees. Now cos of 50 degrees here, the adjacent side becomes p, the hypotenuse is 1. So this is p over 1. All squared, which is just p squared. Easy. So can you see, working out these angles prior is great. So substitutions and the answer, or 2 marks for the answer only. So this is 5.1.3. We've got cos of minus 80 degrees. Now, cos of a negative angle means it's an angle in the fourth quadrant. Cos is positive, so this is cos of 80 degrees. Now 80 degrees is 2 times 40 degrees, so this is 2 cos squared 40 degrees minus 1. I'm choosing that double angle expansion. So again, you're going to deal with double angle identities here, or even compound angle identities sometimes. So let's substitute cos squared 40. It's going to be the adjacent, which is 1 minus p squared over 1. Then we are squaring. So this is 2 into 1 minus p squared minus 1. This is 2 minus 2p squared minus 1. This is going to be 1 minus 2p squared. Here, anyone could have chosen any other path, but sometimes it always helps to keep things as simple as possible. What is this? So this expansion is important, and that answer is important. And obviously, we can give an extra mark here for substitutions or for that reduction. It's not a big deal. So that is the story here. Fairly standard stuff. Let's move on to 5.2. Then we are given tan of x into 1 minus cos squared x plus cos squared x is equal to sine x plus cos x into 1 minus sine cos x over cos x. Okay, now let's inspect here. What we see is that the angles are all single. Now that gives us a nightmare, because to prove a simple expression into yet another simple expression, we need to be cautious. This is no standard question. Now, we can see here that technically if we FOIL this out, we get how many terms? 1, 2, 3 terms. But this numerator is giving us the vibes that, look, if these are all single angles, look at this sine cos x. It's not related to the others per se. So this is giving us the impression that we probably factorized by grouping here. And for that to happen, and we've got 2 terms in each bracket, it means we had about 4 terms in the numerator over just this term. So this already tells us that we need to start here, because we've got squares and there are no squares here. So the most complicated side is that side. So 5.2.1, we can say the left hand side is such that (10x into 1 minus cos squared x plus cos x. Now we can see that here we need to play a very long game, because we need to create as many terms as we can on this expression so that we have at least 4 terms, so that we can try this factorization by grouping, and perhaps it's going to work. Obviously, we are still using our 3-step approach: BODMAS, factorization, identities. So this is a very good exercise because it gives you direction. Okay, so let's do this. Now we're not going to try and use, this is a, this is a square identity. This is effectively sine squared x. But because we want as many terms as we can, we are going to FOIL this out instead. This is going to be 10x minus, we can say this is going to be 10x cos squared x. This is cos squared x plus, now we want 4 terms. Cos squared x is a square identity in a way. So we're starting with identities here, and then we are starting with just dealing with brackets or multiplication in general. So we started here, we are there now. This is going to be 1 minus sine squared x. So can you see we have how many terms now? 1, 2, 3, 4. So we have at least 4 terms, which is our target. Because if we can get 4 terms in the numerator, we are more likely to win. Okay, so this is fine. Again, we can see now 10 can be changed. We're using identities again. 10 is sine x over cos x minus sine x cos squared x. This is over cos x plus 1 over 1 minus sine squared x over 1. Okay. Now what do we do next? The next step is to find the common denominator. The common denominator is thankfully cos x. So now we have our cos x. Then cos x divided by cos x is 1 times the numerator sine x minus, this is 1 times the numerator sine x cos squared x plus. Now cos x divided by 1 is cos x times the numerator, cos x minus. That is going to give us sine squared x cos x. Okay, great. So we keep moving. Now we can see we want to factorize by grouping. Now we need to be smart in our grouping because we want that numerator to come out. Now this simply says we can take this term here. We can take that term that has a sine squared and group it with sine x. And then we can take cos x to lead because we want to create that environment, minus sine x cos squared x all over 1. Not 1, but cos x. Losing focus there. Now let's try to factorize. First, we take the highest common factor between those neighboring terms. This is sine x. Now this is 1 minus sine x cos x, plus here we take cos x. What we remain with is 1 minus sine x cos x all over 1. Not 1, but cos x. All over, Joe. I am all over the show, indeed. Talking nonsense at the same time. Now let's have a look here. Can we see now that we have a common factor? This bracket is essentially common to both terms. So we can take it out as a common factor. And when we take that bracket out as a common factor, things are just touching on their own. What do we remain with? With sine x plus cos x, catching. And then this is 1 minus sine x cos x, catching over cos x. So that is equal to the right hand side. The identity has been proven nicely. So here it just needed us to inspect. Like I always tell you guys, inspection, the doctor's approach is the best. Then you couple that with the 3-step approach, you're going far. Because look, now we stayed with factorizing by taking the highest common factor more than once. All right. Okay, so let's see, where are these marks? Basically, whenever we use any of these 3 steps, which is this part here. So this part, when we used our square identity to expand that into yet another bunch of terms, that's a mark. Great. And then using the 10 identity in a way, maybe I should have marked this one differently. This is marked here so that we don't create confusions. That's a mark. And then using the 10 identity, that's another mark. And then here, trying to use our DM section, AS section, so to speak, we can say this is a mark on its own as a whole. And then factorization is also a mark, and this further factorization gives us a mark. So I think that's how those 5 marks are scored. Let's move on, guys. It is done. So 5.2.2, it says, for which values of x in this interval minus 180 is to 180 will the identity be identified? So, well, we know that the denominator has to be 0. And then this implies that our x is going to be equal to plus or minus shift cos 0 plus k times 360 degrees, where k is an element of integers. This implies that x is equal to plus or minus arc cos of 0 is 90 degrees. That is the acute angle. Okay, it's not acute, but it's a first quadrant angle equivalent, plus k 360 degrees, where k is an element of integers. Obviously, we can see here that minus 90 and plus 90 fits in this domain given. That means k must be 0 here. So we can say, therefore, our x is plus or minus 90 degrees when k is 0, because anything else will give us angles outside that domain. Okay, that's easy. So 2 marks for those two solutions, the positive and the negative. And for stating that cos of x must be equal to 0 for this to occur. Easy stuff. Let's go for 5.3. 5.3, we are given this expression, sine of 150 plus cos squared x minus 1 all over 2. And without using a calculator, simplify the given expression to a single trigonometric ratio in terms of cos 2x. Okay, we're already told the target, not a problem. So 5.3.1, what do we have? Sine of 150 degrees plus cos squared x minus 1 over 2. Again, simplification, 3-step approach. Now first, BODMAS, reduction formulae. 150 is big, so we need to reduce this. This is sine of 180 degrees minus 30 degrees plus cos squared x minus 1. So this is 2. And then this is going to be sine of 30 degrees because sine is positive in the second quadrant. This is all over 2. And then sine 30, it's a special angle. Again, see, we are doing the AS part. Sine 30 is a half. Plus cos squared x, we can say this is over 1 minus 1 over 1. Let's expand this out, divided by 2 over 1, so that we can handle this nicely. On the left hand side, we look for the common denominator, it's 2. Then 2 divided by 2, it's 1. 1 times the numerator, it's 1. Plus 2 divided by 1 is 2. Times the numerator, it's going to be 2 cos squared x. 2 divided by 1 is 2 times the numerator, it's minus 2. We can convert this to its reciprocal when we multiply. Now, we sort out like terms. AS, 1 minus 2 is minus 1. So this is 2 cos squared x minus 1 divided by this multiplied by that, it's 4. Now we can see that after all has been said and done, the numerator is a double angle identity of cos expanded. So what does that mean? We come back to identities. This is going to be cos 2x over 4. If we factor out this quarter, this simply multiplies cos 2x. That's a bit better. Okay, so we've done it, guys. Not a big deal. So where are the marks here? Obviously, knowing this reduction is important. Anything that results from using those 3 steps is mark weight. That's why I'm teaching you this, so that you can see where to score marks even when you don't finish. If you follow this pattern, you're not going to lose marks along the way. Perhaps you will lose for the final answer. Anyway, let's keep going, guys. Now this step here, using or treating this as, fractions like as like terms and stuff, using the common denominator and all that, this is more like doing like terms, fractions. That's a mark. And essentially flipping this, because this is now doing DM section, which is multiplication, but perhaps not there. Maybe the mark is here when we finally did the multiplication, and the other mark is when we contract this to the cos of 2x using identities. That's 4 marks. This one is essentially the same as that, so I would say here handling like terms on the numerator. I don't know, guys, sometimes the marks are a bit cumbersome in placing them, so not a big deal. That's the 6 marks. Oh, it's not 5, it's 6, so it's 1, 2, 3, 4, 5. Now perhaps say factoring here again, maybe extra mark. Okay, so 5.3.2. We now have to find the general solution of this expression. So we write it out. This thing likes to touch itself. I don't know, it was supposed to be touch insensitive when I'm writing, but now it's starting to act up. All over Joe. Now this implies, we know that we reduced this to just a quarter times cos 2x. This is equal to 25, 1 over 25. Then when we divide throughout by a quarter, we get cos 2x is equal to 4 over 25. Okay. Nice and easy. We can say this implies that now 2x is going to be plus or minus arc cos of 4 over 25. Okay. Plus k times 360 degrees, with k as an element of integers. This implies that 2x is plus or minus. Let's do that in the calculator. Shift cos 4 over 25 gives us a 80.79 degrees plus k times 360 degrees, where k is an element of integers. Therefore, x is, now let's divide that by 2. This is 4 plus minus 40.40 degrees plus k times 360 divided by 2 is 180 degrees. Where k is an element of integers. So now that's the general solution, guys. It's as simple as that. Usually there's plenty of solutions here, because someone, remember minus 40 is an angle in the 4th quadrant. So someone may say 360 minus 40.40 and end up with some 300 and stuff, Yeah, 320 some change here. It's gonna come out of 15 or whatever. So if you use the reference angle, you may end up with some big angle there and an acute angle, obviously. But the positive version of this angle is an angle in the first quadrant, so it still works. So we're scoring how many marks? 5 marks here. Obviously, knowing that we're going to reduce this to this is important. And then here, using our gymnastics is important, and then we get 2 marks for those 2 solutions. That's 4 marks. Maybe sorting this up so that we can do that. It's the 5th mark. Easy, 26 marks, guys. So I'm sure my students were like eating this thing and saying this is so scrumptious. Let's just do it. Let's just do it. Probably the problem could have been that identity. Yeah, that one can catch you off guard if you don't do the inspection. If you don't do what I teach you guys, you're gonna cry. Now, we're told in the diagram, the graphs of f of x equals cos of x plus a. So we can see this is a horizontal shift of a cosine function. The amplitude is 1. So that means the maximum and minimum are going to be 1 and minus 1. So there is the maximum, there is the minimum for our function f. Okay, but now if we look at this graph, we'll see that the maximum was meant to be at 0, meaning 0 was supposed to give us 1. But now you can see that the maximum has shifted to 45 degrees. So this already tells us a is minus 45 degrees. Because when we shift our graph to the right, it means in the equation, the sign is negative for that shift. So easy stuff, guys, easy stuff. Otherwise, you can see the coefficient of the angle is 1, so the period is still 360, nothing changes. Okay, g of x is equal to sine 2x. Again, the coefficient of the angle is a 2. So this means the period shortens. It's going to be the original 360 degrees divided by 2, which is 180 degrees. So if we look at this graph, the sine wave is complete here from 0 to 180 degrees. Can you see that? So that is great. That is great. So we just shifted the frequency, meaning what would happen at 180 will happen at 90. What happens at 90 happens at half of that, 45, and so forth. Now I've taught you how to interpret graphs and how to work on them. So also use the knowledge of functions here. There's no excuse for getting things wrong. This is usually the easiest section or question. You must take all the marks. Okay, we're given the domain. We're told you the graphs intersect at n, minus 75 and k, p, 45 and 1, and then q, 165 and k, and p is also the turning point of both graphs. We can see that. So that is fine. We understand our graphs nicely. There's nothing to waste time on here. We can just start answering. 6.1. Write down the period of f. Coefficient of the angle is 1, so it remains 360. So we can say the period t is equal to 360 degrees. 1 mark. 6.2. We need to write down the amplitude of g. Now amplitude is from rest position to maximum, right? So that's 1 unit. So the amplitude is equal to 1 unit. Remember, this is a distance, so you must not just write 1. It's 1 unit. Is 1 unit. Get a mark. So be careful of these things. But perhaps maybe if you didn't write it here, it's safe because it's a coefficient anyway. So a coefficient, we never really write units, do we? Yeah, probably I'm just being overly excited. 6.3. Write down the value of a. Again, it says write down. We realized it. So we know that A is minus 45. It's minus 45 degrees. And then we need to calculate the value of K. Easy, the y coordinate of N and Q without the use of a calculator. So let's see. 6.4, we have the function. Perhaps G is the easiest to apply. Let's use G. So we can say G of x is sine 2x. So we can use any one of these functions. There's no excuse. So let's go on. With that point N, let's take point N. Minus 70 is to K will be such that K is equal to sine of 2 into minus 70 degrees. This implies that K is going to be sine of minus 150 degrees. Is it 150? 2 times 70, it's 140, man. That's 75. Yewena bhalezo ngiqalami kanti yeheni nanko umuntu efuna ukucommit suicide. Okay, so this implies that K is equal to, now sine of a negative angle is going to be minus sine, because this is an angle in the third quadrant. So now we're going to use our reduction formula. This is the same as 180 degrees plus 30 degrees. Yaqoka. 150. It's 180 minus 30 degrees. That's the second quadrant. This also implies that K is equal to minus. Now sine would have been positive, but because it's dragging a negative already. So ngoba seke limele usine. Ay makasele seke limala, uzaseke nezigazi vele, so somenze njani. So asimiyeke limele. So here we can see, guys, that therefore okay word sine of that, it's a special angle, so it's going to be half, but that becomes minus half. Nice and easy. So that is exactly what we were supposed to do. So obviously, guys, this is the story here. Knowing that this is going to boil down to minus sine of 30 and then use our special angles was key. The rest was just a means to an end. So fine. So 65. We are told to calculate x if g of x is, okay, g of x plus 60 degrees. Can you see? Now when you add 60 degrees, that's a shift to the left by 60 degrees. And we're doing the same to f of x and shifting it to the left by 60 degrees. And we are supposed to find this point between minus 45 and 0. Can you see? Obviously, where are these graphs equal? They are equal here at P. So that means we just shift point P 60 degrees to the left, because we are doing it to both and yet they are equal. So within this region, it's that point P. So we can say here x is going to be equal to, it said calculate. Okay. All right, but it's just one mark. I don't know how on earth. So we can just say x is going to be equal to 45 degrees. When we shift to the left, we add 60 degrees. When we shift a point directly, this is no longer, I mean, we can see in the equation it comes out as positive, but directly when we take a point, we're going to say maybe let's start by saying that f of x, g of x must, I don't want this. G of x is equal to f of x at point P, which is 45 degrees, is to 1. All right? When x is an element of minus 45 and 0. Okay? That is the story. We can say now, then, g of x plus 60 degrees is equal to f of x plus 60 degrees is such that x must be equal to 45 degrees minus, in the physical point, we shift that point to the left 60 degrees, so we'll subtract the, and we're not supposed to find the coordinates per se, but just the x. So therefore, x is going to be 45 minus 60. 45 minus 60 is minus 15. And x is definitely in that domain. Can you see? It's less than 0, greater than apha maningabhali into ezingekho apha. Masiziyeke ezazinto. Masiziyeke ezazinto. Okay. So that is the story, guys. That is the story. That is the story. So these questions are fairly easy. So you see, knowing transformations, as you would know them elsewhere when dealing with functions, and then knowing how to shift an identifiable point, we sort it out. Now, guys, that's it. So we're getting just 1 mark, but the question said calculate, so there has to be some show of calculation here. And I always show everything so that even if someone is like, what are you doing? Did you copy this or what? Can just know, but there's no chance of taking me down. Now, without using a calculator, determine the number of solutions. Can you see number of solutions to the equation? Okay, so we're given square root 2. Ndingabi nayo a tendency yokuba consistent. Square root 2 times sine 2x is equal to sine x plus cos x is equal to ayi thatha isingesi sesixhosa ke ngoxelela ndiyakuxelela. So kule, so we need the number. Can you see? They didn't say what are those solutions, but how many are they? Between minus 90 and 90. Clearly show all the workings. So, folks, this is super stuff. This is super stuff, you know. The way I see things sometimes is the way that I see them. You know what I think I should do here? Obviously, this is a root 2, so this is already giving me the vibes of what we call the vibes of what is this thing now? Special angles. So let's just divide by the square root 2. We can do whatever we like in maths. Now that means this is going to be sine 2x is equal to sine, maybe let's just already put it nicely and factor it out. This is 1 over root 2 sine x plus, then that is going to be also 1 over root 2 cos x. What I'm getting at is to try and make everything look like a sine identity, right? This implies that sine 2x is equal to, now if I want to make this a sine compound angle identity so that it's going to be sine, this is the same as sine x, which is that times, root 1 over 2 is the same as cos 45 degrees plus, here I can start with cos x and then say this is sine 45. Smart work, Bafanas. Now we can see this is a compound angle expansion of sine, so we contract it. This is going to be the first angle plus the second angle. Can you see? Now let's go. If sine of 2x is the same as sine of that, then it means these two angles are equal. So we know that 2x is equal to basically x plus 45 degrees plus k times 360 degrees or 2x is, remember for sine we consider two angles, 180 degrees minus this x plus 45 degrees plus k times 360 degrees, where k is an element of integers. Okay, some stories are starting to happen there. So we can already see there that the first solution will transpose x to the other side. We get x is equal to 45 degrees plus k times 360 degrees, or x is going to be equal to, now 180 minus 45 is just going to be 45 degrees, then minus x, then x to this side, it becomes 3x. Okay, and then we have again plus diagonal 180 minus 45 is 135. It's 135 degrees plus k times 360 degrees, where k is an element of integers. So using general solutions, guys, is no, in fact, it's the safest you can ever do. It's like how many people love to use the quadratic formula as safe. This is as safe as that quadratic formula. Obviously, like in the quadratic formula, one needs to maintain vigilance in the substitutions. Same stories here. So this one is done. Now here we divide by 3, x is equal to, divided by 3 there, that is 45 degrees plus k times 120 degrees now, where k is an element of integers. Injalo lento. Now, we needed to find the solutions. So we can say, therefore, x is equal to this set. Obviously, between minus 90 and 90, 45 is the answer, right? Because it's going to be 45 when k is 0. What other solution can we get? Let's now say k is 1. If k is 1, this is already greater than 90 degrees, so it's out. When you say k is minus 1, that is very interesting now. Obviously, this one is out, but this one might do something. 45 minus 120 is minus 75. So we can start with the smaller city. This is minus 75 degrees and 45 degrees. And that should be it. Okay, so you see, general solutions protect you big time as long as you know Once you finish your general solutions, you use your integers to locate where the solutions are. We can say, therefore, there are 2 solutions. Because the question was how many solutions, we needed to first identify them, then count them out. Nicely. Okay guys, so that is essentially the story. Now, how many marks is this thing here? 4 marks. So obviously this is a mark, and locating those solutions is a mark. And but I think the solutions themselves is not the big deal, but perhaps the general solutions. The general solutions, 2 marks. And essentially, when we contracted these compound angle identities or used special angles, I do believe that this is a mark and that is a mark. The rest is your own problem. 3-step approach, guys. Cannot overly emphasize that. So that's how these 10 marks could be scored. Perhaps this could challenge some students, but yeah, maybe slightly higher grade, not necessarily really that great. But yeah, to know what to do here could be a bit elusive. Let's finish up, guys. I thought I could finish this in 30 minutes, but you know, most I talk more than I'm supposed to do. Now, in the diagram, ABC is drawn. AD is drawn such that AD is perpendicular to BC, okay? Use the diagram above to determine AD in terms of sine B. Okay, that's easy, because now we focus on this triangle. So we have to focus on that yellow triangle. You can see it's a right-angled triangle, and we need to represent AD in terms of sine B. So that's easy. So we can say 7.1 with 7.1.1. We know that in triangle ABD, we will see that sine of angle B is equal to the opposite side AD over the hypotenuse side AB, okay? And then this is over 1, cross multiply. Therefore, we can see that AD becomes AB sine B. This is when you're proving the area rule, by the way. So this is how it's done. So they're making it easy. They're making it easy because they could have just drawn this triangle ABC and then say prove this. Then you have to make your construction and then do your things. Anyway, 7.1.2, it says, hence prove that the area of ABC. See, this is proving the area rule. We know that area triangle ABC is going to be half base times height. Half the base is BC, and then the height is AB. Perhaps we can say AD, which is going to be half BC into AB sine B. That's done. So the area rule is proven like this. So that was just easy stuff. So most likely that and that. And essentially here what matters is substituting AD. That's the 1 mark. Okay. 7.2, quickly guys. Trig is the longer section as well. It's like analytical geometry. It's terrible. In the diagram, points B, C, and D lie in the same horizontal plane. That is shaded. Now ADB is alpha. So there's our angle alpha. We can see it. is equal to ACB. ACB, again, we still have our alpha here, equal to alpha, and CDB. CDB is theta. So there's our angle theta right there. And DC is equal to K units. Okay. BD is equal to BC, meaning this is an isosceles triangle, and that means if that is theta, that angle should also be equal to theta. Okay, so now with this 3D diagrams, guys, we know here we need to know where to start, and obviously inspect as much as we can. Where we start, it's a triangle that we have the most angles and a given side. Then we work towards a common side to some triangle that has what we are supposed to find. Okay, that's usually the strategy here. Now it says prove that AD is equal to AC. Okay, that's not a big deal. So how are we going to prove that? Yo, saqhelwa kakubi nje ekuseni kuvukwa namadoda. Ekuseni kuvukwa nje 2 marks cha ayikhathi ndicinge. So ithini nalanto AD maske sibone apha, because these are the two triangles. So if we look at those two triangles, do you realize that these triangles are congruent? Because this side is common, and then this side is already given to be equal to that side. This angle is equal to that angle. That angle is equal to that angle. That only means those angles are also equal because they are the remaining angles. So if these triangles are congruent, AC should be equal to that. These are the corresponding sides in congruent triangles. But we can use the right angle hypotenuse side business there. Yeah, but I think the hypotenuse side is what we want to prove, so we can't use that rule. Okay, let's see. We can say here 7.2.1. In triangle ABD and triangle ABC, we see clearly that DB is equal to BC. That was given. Okay, so this is Euclidean geometry now. Enina kodwa ntene ndidlala ngabanye abantwana sithi ke ngoku AB is common, right? And let's use the included angle instead of going around in circles. We can say ABD is equal to ABC equal to 90 degrees given. You can say therefore triangle ABD is congruent to triangle ABC. Reason, this is side, angle, side. Okay, SAS. This is the so-called spinal subarachnoid space. Yawena, so spaphela son. Telling ngati uyaspeeda boy. Spinal subarachnoid space. Idoni yona leyo. Iyo yona londo eyiyo. Qhelakabi. Anyway, we can then conclude. Therefore that AD should be equal to AC. These are the corresponding sides of congruent triangles. Done. So a Euclidean geometry question was thrown in here. But to prove, by any means necessary, because I know imaths son inemikhuba yovela ifike nje ungayilindelanga nje. So guys, I think what was important was to prove a congruence, that statement and reason. And this last one, the reason for why those two are equal. Because those ones were fairly given, so there's no marks for those statements. You didn't discover them, they were volunteered to you. So 7.2.2, it says prove that BD is equal to K over 2 cos theta. Now where's BD? This one. So technically, if this involves K, it means we need to calculate this angle. That's going to be 180 degrees minus 2 theta. Simple as that. Okay, so remember, you always calculate all the possible angles as well in these diagrams. After knowing where to begin, you calculate all angles. But we can deal with this. We can say in triangle DBC. Kwenzakalani, but we know that that angle DBC is going to be equal to we can say angle C in this triangle is equal to theta. Oh, turning papa nje ngoku. Senibhale izinto ngokwesibhangqa. And angle D. Remember, I stated the triangle. I don't need to use CDB, this business and that business, equal to theta. The reason here is these are angles opposite equal sides, given that ODB is equal to OBC. So guys, go through the motions. Remember, don't be complacent just because you're in another section. That's why you lose marks. You always think sections don't overlap. Here when uzozwa ngathi uyasha. Sizothi ke ngoku then we also know that also this angle DBC is going to be equal to 180 degrees minus 2 theta. This is sum of 3 angles of a triangle. We're still talking about the same triangle. And then we can go on and do the business. Now that we know what we know, we can use, now what do we want? We want BD. So we can say sine rule. BD over sine, the angle opposite that, which is C now. Can you see? Is going to be equal to, we want DC to be used over the angle opposite that, which is DBC. Why is that? This is the sine rule. This is the sine rule. So let's substitute BD over sine theta, that angle is theta, is equal to DC, no, DC is K, over sine of 180 degrees minus 2 theta. Okay. Then we just cross multiply the sine there. We can say therefore BD is going to be K sine theta over, now this is a reduction story, sine in the second quadrant is positive, sine 2 theta. And then we see that this is K sine theta divided by, this is a double angle identity for sine. We expand and then we see that those guys do it. They do it. K over 2 cos theta, and that's what we wanted. So again here, simplification of trig expressions, so is still applicable. So don't think it's over. It's not over. It's not all over, Joe. It's still one. It's still one. So essentially, guys, I suppose this angle was key. There's no running away from it, right? Right. Once we have the angle and we identify the sine rule and substitutions is key, this double angle expansion is also key. The rest is what was given. So 3 marks is fair enough. So masenzeni ke ngoku the last one, 7.2.3. Okay, so we are told to determine the area of BCD. BCD, this triangle, in terms of K and a single trigonometric ratio of theta. Okay, so that is good because we know those sides are equal. We know the included angle. Maybe we can use that. Let's just try that out. In triangle, they called it BCD. Okay, so what do we see there? We know that the area of triangle BCD is going to be equal to half, using the area rule, of DB times BC sine of the included angle DBC. This is the area rule. Okay, that is the reason. So this is half. Now we know that BD is K over 2 cos theta, so this is K over 2 cos, that's 16, and that's 17, K over 2 cos theta into BC is the same, K over 2 cos theta sine of 180 degrees minus 2 theta. Alright, so that means the numerators multiply. So this is going to be basically K squared times, we reduce that, it's going to be sine of 2 theta. All over. This one becomes 2 times 2, 4 times 2, it becomes 8 cos squared theta. Okay, so this becomes K squared times 2 sine theta cos theta divided by 8 cos squared theta. So the square takes that cos, 2 takes that one also. So what do we have here? We've got K squared times sine theta over 4 cos theta. So this is K squared over 4 times sine over cos is 10 theta. So that is a single trigonometric ratio. Alright, so that was easy, guys. Easy stuff again. Area rule, very important. We can use it there and say the substitutions essentially. But then when we had to expand that double angle identity, it was important because the reduction, we've done it above, so we can't mark it. And essentially using our 10 identity here to get to that. So that is how those 3 marks are scored, and that's how the 11 marks should be taken. So again, fairly standard stuff, nothing really out of the ordinary. So you can see here I took 1 hour explaining the Euclidean part, 1 hour explaining this one. So you've got 2 hours in, and if you did it nicely, you know that you've got 75% in the bag, right? Okay, maybe I'm lying. Yeah, most likely around that much. And then we have now statistics, which is a quick stuff. You can do it in 20 minutes. Analytical geometry, the first question can be done in 20 minutes. And that means the last question, you can do it for the remainder of the 40 minutes, so to speak. Is it 40, 20? It's another 20 minutes. Yeah, that could work. But obviously, you are not explaining anything to anybody like I am doing. So you just go about what you know and you just run into it. So you might even have some minutes to spare to double check your answers and get your stuff in order. Okay guys, I hope you enjoyed the video. I'll see you some other time. Bye bye.